Steinhauer here. Welcome back. We are continuing our journey through the universe, but let's pause briefly and ask a review question over the material we went over last time. And this review question is, why are astronauts in space, say on the International Space Station or on a rocket that is orbiting the Earth, why are they weightless? Why do they experience no, they float basically in their space pod. They don't exert any forces on a scale if they were to stand on it. Is it A, because there's no gravity in space? Is it because they're constantly in free fall around the Earth? Is it because the gravity of the moon and the Earth cancel each other out? Or is it because of aliens? Make your guess. Okay, we discussed this quite a bit last time. This is an important thing. It is not that there is no gravity in space. If there were no gravity in space, it would be that orbiting the Earth was impossible, right? If you had an object, let's say a satellite or a space station that were here, and there were no gravity in space, what would its orbit look like? Well, it would not circle around the Earth. There must be a force. That's a change in velocity. There must be a force if there's a change in velocity or an acceleration. And therefore, if there were no gravity in space, then this object would just continue in a straight line at constant speed, right? That is Newton's first law of motion. In the absence of a force, objects tend to move in straight lines at constant speed. There is gravity. There's gravity because the object is orbiting, right? The object actually takes a path that looks like this. And that's because the gravity of the Earth is keeping it there. So why are astronauts weightless in their space station? It is the same reason why you are weightless in an elevator when you cut the cord. And both the elevator and the person are free falling through space until they hit the bottom. In a spaceship, it works exactly the same way. You're in an elevator, it's just that elevator is moving fast enough that it never hits the bottom. And so the elevator or the spaceship is falling at exactly the same rate as the astronaut is, and therefore it seems like within that there's no actual forces acting on the astronaut. Okay, so the answer is they are both constantly in free fall around the Earth. Great. So moving on, this week's topic is radiation and spectra, or even better word for it would be light. And this is all in chapter 5. Now, light is really, really important in astronomy. Understanding how light interacts with matter is really, really important in astronomy. Why is it so important? Because almost everything that we know about the universe, almost every piece of information that we've gained from things outside the Earth, come from the light that we get from those sources, with very few exceptions. We'll get into some of the exceptions because they're interesting as we go along. But almost everything we know about other planets, about our sun, about other stars, about galaxies, about black holes, about anything that you could think of in astronomy comes from the light that we get from those things. And so understanding what light is, how it's generated, how we detect it, how it's different from source to source is very important, understanding how we know about those sources themselves. So chapter 5 is going to be on the light itself and how it interacts with matter. So here's a preview question for you. What happens when you see something? Here is your eye down here. Light's interacting with your eye to see something. So what do you think? Is it that light enters your eye? Is it that light exits your eye? Is it that something enters your eye but it isn't light? Is it that something exits your eye but it isn't light? Again, go ahead and make a guess. Write something down. I'm not actually going to give you the answer, but hopefully it will become obvious as we go along what the true answer was. So here's light. Again, Isaac Newton did a lot of experiments with prisms and optics and light, in addition to all the other amazing stuff that he did. And one of the things he noticed, and you can notice if you've ever played with a prism, is that when you shine white light through a prism, you get a rainbow. It was thought before Newton's time that the prism was adding the colors to the spectrum, was adding the colors to the light, and that somehow the light inside there. But in Newton's time or shortly thereafter, it was started to realize that in fact, the white light was made up of those different colors. And so this is one of the things that make light unique. White light, especially from the sun or from an incandescent light bulb, is actually made up of an entire rainbow of colors. And so the question becomes, what makes those colors different? Why do we see those different colors? How are eyes sensitive to those different colors? That is a very prominent part of our everyday experience and understanding of life, right? We walk around and experience everyday life seeing colors around us. This person, for instance, sees the red chair. Why does this person see a red chair? Why does this person see a green tree? It is because this chair is interacting with the light that hits it in such a way that only the red light particles are reflected off of it. It is taking this white light and absorbing all of the colors that aren't red and only reflecting those that are red, and therefore we see the color of the chair as red. This person's blue jeans we see as blue because the jean material is absorbing all of the other green and blue and yellow and orange light and only reflecting the blue light. And so everyday objects appear as colors to us because as white light, which is generally what we have in our ceilings and in the sun, is bouncing off of those objects and only reflecting light of a certain color. So that's our everyday understanding of light and how our eyes interpret that light. We'll talk a little bit more about what light is now, though. What is light? Light is actually an amazing thing, and it is an odd thing. In fact, this still mystifies physicists today, but it turns out that light can act either like a wave or like a particle. And in fact, it can't do both at the same time, but it can do either one. And it can do both at the same time. So let's think about particles. This is an important vocabulary because I'll be using this term a lot. A particle of light is called a photon. An individual particle of light is called a photon. But let's think about the wave-like nature of light first. So it's odd. You think about a wave on the ocean, right? That is not a discrete thing, right? That wave can travel, for miles and miles and on the ocean, and it can extend for miles and miles, a single wave up and down. And so to think about that as a discrete particle is hard to wrap your brain around. And I'm not going to ask you to wrap your brain around it, just to accept that we've made experiments that prove that light can both act like a wave and like a particle. So let's talk about the wave nature of light first. Let's talk about waves first. What is a wave? Well, here's an example of a wave. This is just a line drawing of a wave, right? And you can talk about the peaks of those waves and the troughs of those waves and how it goes through the cyclical pattern of up and down. What that up and down is will depend on the wave. If it's a water wave, it'll be water moving up and down. If it's a wave on a string, it'll be the string moving up and down. If it's a sound wave, it is a compression wave in the atmosphere of air. We'll talk about what is specifically waving in light's case. But all of these waves can be characterized by a wavelength, meaning the distance from a peak to peak or a trough to trough. Those two should be the same distance. Be careful not to choose this as the distance from one midpoint to another midpoint. That is actually half of the wavelength, right? It's only half the wave, the upper part of the wave. You'd have to go to this all the way over here to get a full wavelength. So the distance between two wave peaks or two wave troughs is the wavelength of that wave. Frequency is a little bit harder to understand, but it's a similar thing, right? So this is involved in how this wave is propagating, right? This wave has a direction. So in other words, this wave is moving, let's say, in this direction. And if you were standing here still, let's say at the origin here, you would see this wave passing by you. Sometimes you'd see an up peak, and sometimes you'd see a trough, and sometimes you'd be in the middle. But as this wave goes by, you'd be experiencing the wave as it propagates through. The frequency is how many of these peaks you see in a given time, right? How many of these peaks pass your position at a given time. But frequency is how many of this thing happen at a certain amount of time. That is a frequency, right? So if you're familiar with cars, your tachometer reads revolutions per minute, or RPM. That's a frequency. It's how many times your engine pistons cycle through and up and down every minute, RPM. And that's usually a typical number in the thousands, right? This is peaks per second. We're going to be doing this in per second, but how many of these peaks go by per second, say? And the wave speed is how fast these peaks move through space. So it's the velocity at which this peak, say, moves in this direction. Those are the three things that characterize all waves: how fast they're moving, what the wavelength is, and what the frequency of that wave peaks passing by a particular point is. Great, let's talk about light itself now. Light as a specific wave is an electromagnetic wave. That's a big word, which has obviously electricity and magnetism in it, because that's exactly what it is. It is a vibration of electric fields and magnetic fields. And so why does light interact with particles, and why do particles emit light? Because particles are made up of charged particles, and charged particles interact with electric and magnetic fields. That's sort of all I really want you to know. We're not going to talk about how electric fields work much in this class, or magnetic fields work much in this class, and a very baseline understanding is okay, but that's what a light wave is. It's an oscillating electric and magnetic field. Okay, so let's talk about the specific wavelengths and frequencies and how they're related. Wavelength and frequency and wave speed are all related to one another in a wave, as they have to be, right? For a particular wavelength, the faster that wave is moving, the higher the frequency will be, the more of those peaks and troughs you'll see going by in a particular second. And so wavelength and frequency and wave speed are given by this equation. Lambda, this is the Greek letter, I'm going to put a box around this. This is the Greek letter lambda. I'm going to Lambda. That's the lowercase lambda, which is basically L, which is kind of a way of saying length, right? It's the Greek letter L for wavelength. We use Greek letters a lot in physics and astronomy because we have a lot of different kinds of variables, and it's useful to have to know what they are. So they have different symbols. We still have to use the same symbols sometimes for things, but using the Greek alphabet makes it so that we have more options available. So wavelength times frequency is equal to wave speed. That is this equation. So let's talk about units. Wavelength, again, is a distance. It's a length. So any unit of length is appropriate for this wavelength. We can use meters. We can use yards. We can use centimeters. We can use nanometers, which we use a lot for wavelengths of light because the light that we can see tends to be in nanometers. But any unit of length will work for wavelength. What are the units on frequency? Again, there's always some unit. It's always cycles per minute, or cycles per second, or troughs per second, or peaks per second. But that cycles and revolutions and peaks isn't really a unit, that doesn't have physical dimensions. It's just a thing. You're counting, really. And so we usually, anything that is 1 over time will work. Per second, per minute, per year, per decade. But typically 1 over seconds is the unit we'll use. You'll also see 1 over seconds sometimes written as hertz. That's hertz, H-E-R-T-Z, like the rental car company. So 1 over seconds, you'll say hertz. And that just means how many times per second something happens. Okay, wave speed obviously is a speed. It has units of meters per second, or miles per hour, or kilometers per second, or whatever you want. In this particular case, the speed is the speed of light, obviously, because we're talking about a light wave. And the interesting thing is, unlike many other waves, this is a constant. if you're not in a medium, if you're in vacuum, and in space we're always in a vacuum, this number is always the same. And that number is very big. It's 3 times 10 to the 8 meters per second. We used that before. So that's interesting. Normally you have some flexibility with this formula, right? Lambda times F equals C. Well, you can specify 2 of these and that specifies the third. In the case of a light wave, we say C is the speed of light, and this never changes. This is always 3 times 10 to the 8 meters per second. So you only have one choice, one degree of freedom for your light wave. You can either choose the wavelength, but once you do, that sets the frequency because C is constant. Or you can set the frequency, but that sets automatically what the wavelength is, again, because C is constant. All right, let's do one example where we try out this particular formula. So what is the frequency of a photon that has a wavelength of 600 nanometers? Let me write that down, 600 nanometers. We need to know, first of all, what a nanometer is. What is a nanometer? Again, if you need to look up what a nano is, that's okay, you can. You can see the appendix of the textbook. Obviously, you can look this up on the internet. It's all there. Nano, I'll write this out, nanometers. So meters is obviously the unit, and nano is the metric prefix. And obviously, there are lots of metric prefixes, and they tend to go in groups, in multiples of 3. Nano means 10 to the minus 9. So if I say a nanometer, that means 10 to the minus 9 meters. So I can write this, 600 nanometers is equal to 600 times 10 to the minus 9 meters. And that I've replaced nano, the word nano, with times 10 to the minus 9. And now I've got a number that's just in meters. So 600 nanometers is equal to 600 times 10 to the minus 9. And if you know how, and you can plug this into your calculator and it will work fine. But let's just talk about this, and we can write this in a different way. 600 times 10 to the minus 9, we can move the decimal place, which is right there. We can move the decimal place over 2 digits and make this 6.0. But if we do that, then we have to change your exponent, right? And moving the exponent to the left makes it so that you have to increase this number. Moving it to the right makes it so you have to decrease this number. It makes sense. If you're going to make this number smaller, you need to make this number bigger. Well, if we're going to make this number smaller, this number needs to be bigger. So, and then we need to add the number, which is the number of places we've moved the decimal. So this becomes 6.0 times 10 to the negative 7, because negative 9 plus 2 is 7. That's meters. So these two numbers are equivalent. It's important to know that they're equivalent. Again, for your calculator purposes, you don't need to worry about this. You can plug in 600 times 10 to the minus 9 and be just fine. Okay, so now with this, now that we know what wavelength is, again, this is the Greek letter lambda, we can plug this into our formula, right? We know that wavelength times frequency is equal to wave speed, the speed of light. In this case, we know what wavelength is, and we want to solve for frequency. So let's divide both sides by wavelength. The wavelengths cancel out over here, and we get frequency is equal to C divided by wavelength. So this is 3 times 10 to the 8 meters per second divided by 6.0 times 10 to the minus 7 meters. Okay, so we can certainly, by the way, why are we choosing 600 nanometers? This is a red photon. This is a photon that we can see with our eyes. It's pretty typical for visible light. We'll talk about where that lies in the whole spectrum in the next video. So you can certainly pull out your calculator to do this, but I want to show you that you don't have to pull out your calculator to do this, at least to get a rough idea about what's going on. again, if you're dividing two numbers that have scientific notation, how do you do this? You divide the bases. I mean, you can just plug this in your calculator, 3 times 10 to the 8 divided by 6 times 10 to the 7, and it'll work. But I think it's important to understand kind of how this works, right? You're going to divide the bases and you're going to subtract the exponents, right? So you can get an order of magnitude for what this new number is going to be by just taking this number and subtracting this number. 8 minus -7 is 15, right? So this new number should be something times 10 to the -15, 10 to the 15, 10 to the positive 15. What is that something? Well, it's 3 divided by 6, and that's a half, right? So this is 0.5 times 10 to the 15. Plug it in your calculator, see if you agree, but this is, you don't even really need a calculator to do multiplying and dividing by scientific notation. It works pretty simply. Now, this number has units. What are the units on this number? Well, we've got meters per second on top and we've got meters on bottom. Well, the meters cancel out because I've got meters in the numerator and then the denominator. So all that's left is this 1 over seconds. And so the unit on this thing is hertz, or 1 over seconds. Now, if you want to write this in true scientific notation, you need to move the decimal 1 over to the right, and this becomes 5.0. But if you move the decimal 1 over to the right, you have to make this one smaller, times 10 to the 14 hertz, or inverse seconds. And both of these numbers are exactly the same. So this is a huge number, 10 to the 14. That's a 5 with 14 zeros after it, right? That's how fast light is moving and how short its wavelengths are. A red light that's hitting your eye oscillates up and down as it hits hitting it 5 times 10 to the 14 times per second, which is again, unfathomably large number. Okay, we'll come back in the next video and talk about the electromagnetic spectrum and what different light colors look like and what their wavelengths are. Okay, see you then.